Okay, the next concept that we're going to talk about are the real zeros of polynomials. And I've started you off with an example here that should look very familiar. So we've got a quadratic, which is a type of polynomial, and we know that if we want to find the x-intercepts or the zeros, that we need to set this equal to 0 and solve. So we set it equal to 0. If we can factor, we should, which I've done here. And we know that if we can factor, we've got a times b equals 0. That's the zero product rule, and we can break it up. So we set this equal to 0 and solve. We set this equal to 0 and solve. So some of you have already made the connection between these factors and these zeros. So if x plus 3 and x minus 1 are factors, you should be able to see that every single time when you solve this, the sign is going to change because you move it to the other side, you get a different sign. So if x plus 3 is a factor, we know that we get negative 3 for a solution. And if x minus 1 is a factor, we get positive 1 for a solution. So these are solutions, which means that they're also zeros, which means that they're also x-intercepts. Okay, so we've seen all of this. We know that all of these are true. And the cool thing is that this expands on to other polynomials. So it doesn't matter how many things you multiply together. Okay, if you have 3, 4, 5 things, however many, then you get each factor set equal to 0 are solutions. Okay, and if you set each factor equal to 0, then the solutions that you get from those are going to be the opposite sign of the factor that you started with. So for example, let's say we have f of x is equal to x plus 1, x minus 2, x plus 3. And we want to know what are the zeros. What are the zeros? So we would get x plus 1 equals 0, x minus 2 equals 0, x plus 3 equals 0. And when we solve this, we would get negative 1, positive 2, and negative 3. So what we can do now that we understand this is we can skip directly from this factor to this 0, and this factor to this 0, and this factor to this 0, without having to write all this stuff out every time. We know that that's how it works. Okay, so let's say, let me make a little bit of space here. All right, let's say we want to know what are the zeros of the polynomial f of x is equal to x, x minus 5, x plus 2, and x plus 1. Okay, what are the zeros of this one? So each factor of x should give us an answer. So this one we haven't seen. This one's a little bit different. What do we have if we have an x out front? Well, each thing sets equal to 0, right? So this is the same as x plus 0, or you can just think of it as setting it equal to 0. So for this one, we get a solution of x equals 0. And that's true anytime x is by itself. For x minus 5, we get a solution of x equals positive 5. X plus 2, we get a solution of negative 2. And for x plus 1, we get a solution of negative 1. Okay, so these are our solutions. They're also our zeros, which means they're also our x-intercepts. So we can go between a polynomial and the graph very quickly just by looking at it in its factored form. All right, now going the other direction, let's say we want to find a polynomial. Find a polynomial that has zeros at negative 1, 3, and 2. So we want to find a polynomial that has zeros at negative 1, 3, and 2. So now we're working backwards. So we have the 0, and we want to get the factor. So if we have a 0 at negative 1, we know that we have to have a factor of x plus 1. A 0 of 3 means we have a factor of x minus 3, and a 0 at positive 2 means we have a factor of x minus 2. So there could be other things going on in this polynomial, but we know that it at least has to have these 3 factors. So we would have x plus 1, x minus 3, and x minus 2. And the book will say answers may vary because there could be a coefficient out front, there could be exponents here, but we know that this is one possible polynomial if we have those factors. All right, let's make a little bit of space again and see if we can go back and forth between the graph and the polynomial now. All right, so let's say we want to know if we have, okay, so we have f of x is equal to 1/2 x minus 3, x plus 1, x plus 4. Which of the following could be its graph? Okay, so let's see if we can figure out what the graph of this would be. So our first option, 2, 3, 1, 2, 3, 4. Okay, so our first option is going to be here, here, and here. So we're going to go like this. Okay, there's our first option, and here's our second option. 1, 2, 3, 4. 1, 2, 3. Okay, so you guys know by now my tablet graphing is not super neat, but you should be able to see enough here to decide. Okay, so which of these could be the graph of 1/2 x minus 3, x plus 1, x plus 4? Okay, so first of all, let's try to figure out the zeros here. Does 1/2 affect the zeros of the polynomial? What does a number out front of a function do? Remember back to our graphing section, a number out front stretches or compresses the graph. So this is a stretch or compress on the graph. This does not affect the zeros in any way. So a number out front you ignore. An x out front is important, but a number out front you ignore. From this factor, x minus 3, we get positive 3. From x plus 1, we get negative 1. And from x plus 4, we get negative 4. So we need zeros at positive 3, negative 1, negative 4. So this one has zeros at negative 3, positive 1, positive 4. Could this be a match? No. This one has zeros at negative 4, negative 1, positive 3. Is this one a match? Yes. Okay, so that's the idea there between going between the function and zeros.